Okay, can I start now?
Sure.
Okay. So this is my third and final talk. The topic is Wigner's little group, and for that the necessary materials I have already introduced, and which is nothing but the Poincare algebra or inhomogeneous Lorentz algebra corresponding to the Poincare group or inhomogeneous Lorentz group. As I told you, by itself the Lorentz group is non-compact and translational subgroup is also non-compact. And the Poincare group is obtained by taking semi-direct product with the homogeneous Lorentz group with the translation. All these things I have discussed. Also, Professor Liji has spoken about it today. So I think you should be quite familiar with this now. He has also written down the Poincare algebra again, all for you to see. So let me start with the first slide. Please. Okay. So if you look at the Poincare algebra, you must have noticed the translation part, they commute among themselves. There are four generators, P mu and P mu's, they commute among themselves. So one particle state, if I consider, so you can think of one particle state as I have spoken about it in my first lecture itself. A particle can be described by or yesterday itself, the Poincare, the irreducible irreps of Poincare group can be described by giving the eigenvalues of the Casimirs, P mu, which gives its mass, and the eigenvalue of the W mu is the Pauli-Lubensky vector, which gives spin. We have also seen that to describe spin, we have to necessarily introduce multi-component wave functions. And in non-relativistic setup, we have shown that this thing that you have to introduce two-component spinors to describe the spin half particles. And if you go on increasing the components, it will describe higher spin content, spin part of the angular momentum. Okay. So what is essential is that since this spin comes from the SU2 Lie algebra, so they are indexed by some discrete indices, which take some discrete set of values. So, and P mu, W mu, they commute among themselves. So, any generic one particle state can be labeled by the eigenvalues of P mu, which you call it P mu, and sigma, if any, this the spin part of it will be sigma. So, you anticipate that will be your discrete set of levels. Why I am saying anticipate? Because all the while I have discussed during the first lecture, when I discussed the spinning particle, I considered only massive particle. But now, since the relativistic setting, you are going to encounter massless states also. So you don't know a priori whether it can take discrete set of values or not. For example, when I discussed the whale spinner yesterday, I said that it will have spin with this helicity component plus half and minus half, but I did not say what is the group theoretical reason behind it. Today I will try to see how this thing comes about. So let me start with this one particle state psi p sigma, which is the eigenstate of this P mu operator, is the eigenvalue P mu. And sigma is any discrete level if there is any spin content in the theory. So you see, as I told you, through Wigner's theorem, the translational group will act on these one particle states through unitary representation. And this unitary representation will be necessarily infinite dimensional. As I told you, this is a theorem that non-compact group has to be represented through some infinite dimensional representation. Because after all, if you are to have some finite dimensional representation, it would have been UN, which is compact, and you should not expect to have some homomorphism between non-compact group to some compact group kind of thing. But they're very heuristic. For detailed proof, you can go through mathematical literature, but this is a theorem we'll use. So under this translation, you expect that it will acquire a phase. So under unitary transformation, it will acquire a phase e to the minus I a mu p mu. And since these states are eigenvalues of the p mu operators, so operators are represented by the capital P's and the eigenvalues by small p's. I am not using any hat notation here. Okay, it is about I minus I A dot P. This is a Lorentz 4 vector. So A mu P mu. So that's the way it will go. Okay. On the other hand, under the action of the homogeneous Lorentz transformation, which I denote to be U lambda 0, remember the Poincare group, there are semi-direct product of the homogeneous Lorentz group and the translation group. And translation group is the additive identity is 0, and for homogeneous part it is a multiplicative identity, which is identity itself. So here that's why U lambda 0 I denote it by simply by U lambda, the homogeneous Lorentz transformation. You expect it to act on these one particle states to produce an eigenvalue lambda p, eigenvalue lambda p mu of. So let us show it in the next slide, please. So what I'm doing is that you psi p sigma was an eigenvalue, had an eigenvalue of p mu with eigenvalue p mu. Now you consider u lambda of psi p sigma and consider it the action of capital P mu on this thing. So insert the identity operator u lambda u inverse lambda in front of it. Now you consider the object in the parenthesis u inverse lambda p mu u lambda. By invoking the relation I have derived yesterday, we have seen that under this kind of unitary transformation, they transform the vector operator, and this is given by u lambda lambda mu rho p rho. So now again P rho acting on psi P sigma will bring out this lambda mu rho small p rho, and that will come out because these are numbers now acting on u lambda psi P sigma. So you can combine these things lambda and P, so it will give lambda P whole mu and u lambda psi P sigma. So what you get is that you are indeed showing that under the action of u lambda on psi p sigma, this goes into a state which can be leveled by lambda p. So lambda p mu is the eigenvalue of these things. So these states in turn can be leveled by lambda p as a 4 momentum. But apart from that, you have the other spin indices also. You don't know how they transform under this action. So in general, you expect that the spin components get mixed up. As you have shown in the non-relativistic context, under the action of SU2, different components of the two-component spinner, there's some sound, background noise coming somewhere. Anyway, so that get mixed up. So you expect that the sigma levels also should get mixed up. So you write a general combination of this thing, this object, psi lambda p sigma prime, and you take a linear combination with coefficient sigma c sigma prime sigma. Okay. So you expect that this should furnish a reducible representation of SO1, 3. Okay, and psi p sigma will be the identified the state of specific particle states. You see, in general, what happens is that in the most general situation, you may have this may give you some reducible representation, but what we are assuming is that C lambda sigma prime sigma will furnish some irreducible representation. If you were to get some other irreps, that will possibly will correspond to some different species of particles, so which I am not considering here. So here I am considering the irreducible component of these things. Okay, please go to the next slide. So now, you see, what are the invariants? The p square, which is eta mu nu p mu p nu, in our signature convention is negative definite. Means it can be exactly 0 for massless particle, otherwise for massive particle is strictly less than 0. The sign of p naught are invariant under the proper orthogonal Lorentz group, because we are not considering time reversal transformation. Also, we are not considering space reversal or parity transformation. So take once, means since these are invariant, you may ask the question, can I write down any p mu 4 vector which can be in general be null vector, p square is equal to 0, or it can be a time-like vector. These are two physical cases we will consider. We are not going to consider any non-physical cases. So massive particles or massless particle will be considered. So these are the two scenarios. So we are asking whether there is a standard force vector k mu can we find such that all p mu's can be related to this k mu through some Lorentz transformation. The answer is yes. It is something analogous to, you recall, your SO3, the orthogonal group in 3 dimensions. Orthogonal group in 3 dimensions act on any unit vector on S2. S2 means a sphere, 2-dimensional sphere, and you can connect any point of the sphere to any other point of the sphere. We say this group SO3 acts transitively on S2. That means any pair of points can be connected by suitable SO3 point. But there is no unique choice. For example, you may consider 1, 0, 0 is a point where x-axis intersects the unit sphere, which is whose origin is at the origin of the xyz plane, the axis space. So, if you consider another point, say at the where y-axis intersects the sphere, so its coordinate will be 0, 1, 0. Now you can go to from the point where x-axis intersects to the y-axis intersects the spheres through simple SO2 rotation around z-axis along the equator. Okay. Somebody else may say that no, I'll go along the lines of longitude, first of all to the North Pole, and then come back from the North Pole along some other meridian to come to the y-axis. That is another possible route. Both the groups, you can see they are different SO3 groups, but they differ by some, because if one you call it G1, another is G2, you can easily convince yourself G1, G2 inverse will be some SO2 group which preserves some point on the sphere. So typically this will give you stability subgroup. So here also, if you consider all massive particles of the same mass, that means they belong to some same mass shell, all the points p mu, if they correspond to momentum, can be connected by some Lorentz transformation from some fiducial choice. This choice you can make arbitrarily, but to identify what sort of group that is working behind these things, it will be better to choose some convenient one, as we will show below. So you can apply this Lorentz transformation, which is proper orthogonal group. You can find many of them, infinite number of them practically, which connects this p mu to some given fiducial force vector we have chosen in some appropriate and convenient manner. So you can now think of that if for the one particle states likewise, if the states are leveled by k sigma, psi k sigma, under the action of the unitary counterpart of this Lorentz transformation L, if you consider ULP, so ULP will act in this one particle state, will generate some momentum P for you, which will be leveled by P now. And by definition, I am taking it to be sigma again. I am not considering here this a linear combination of sigmas. It is by definition, whatever be the state you get, I label it by sigma, the original spin index that is you have started with, which occurs in the along with k in the psi sigma. And NP is some normalization constant that I'll talk about later. Okay, so this is the thing you expect. Okay. Let's go to the next slide. So now you consider action of u lambda on psi p sigma. So NP being a constant number, it will come out. U lambda will act on this thing, u lambda, u of LP psi k sigma. Now you can apply the group homomorphism property. You can write it as NP times u of lambda LP acting on psi k sigma. Now you insert, which I have indicated by some red color, that you insert an identity here. That is u L lambda p, u inverse of L lambda p. And then in the next line, what you are doing, u inverse L lambda p, you are clubbing with this thing, u lambda of LP. Sorry. Lambda of LP. Now you see this L inverse of lambda p, lambda LP is what we denote by W lambda P, because both it has got dependence on both lambda and P. Now, what it does to when it acts on what it does on its action on K nu, you can easily see that from K you are coming to a 4 vector P, and then lambda will take you to lambda P. L inverse of lambda P will back to K, but you don't know whether you are going to come back to the same K or is up to some stability subgroup. That's the point I mentioned. You consider the example, simple example of the sphere. So this is a non-trivial group. It's even if, or you can see another way in the case of sphere also, you can say move from one point to another point, and after reaching that point, you can further subject the vector to another SO2 rotation around an axis passing through that point. It is not going to change because it's a stability subgroup. So there is an ambiguity of this group here, and this is in this context from massive particle or massless particle, we'll call it the Wigner little group. The structure of this Wigner little group would differ in this case for massless or massive particle. So we consider these cases one by one. Okay, so W is the Wigner's little group, which is a subgroup of the proper orthogonal orange group, which preserves this 4 momentum K, and is known as Wigner's little group. We'll see that it's very, very important in the description of transformation property of one particle states under arbitrary Lorentz transformations. Okay, go to the next slide, please. So now consider the action of the W, the Wigner little group, I just said W, on the state space, one particle state space. And one particle state I have taken to be psi K sigma. K is the fiducial 4 vector I have chosen to work with. So under the action, again the action has to be through some unitary operator, U of W acting on psi K sigma. It will be give rise to some vector K itself, but now spin components will get mixed up. So it will give you some matrix element D, and whose rows and columns are labeled by sigma prime is sigma. Sigma prime is a dummy index. It has to be some like this. You can check these D's furnish a representation of this little group. Not only that, these metals determine the representation of the enlarged or bigger homogeneous Lorentz group, for which this W is actually subspace. So how to see this? You just act by U lambda on psi P sigma. Now, what are you doing? Psi P sigma we had already seen. It is like this: NP U of L lambda P, U of W lambda P, psi K sigma. Now, using the above, the first equation in the above this thing, I can write the action of U W lambda P on psi K sigma as these things. D sigma prime sigma W of lambda comma P. You see here now additional levels lambda and P are coming in the argument of W. These are big numbers. I can extract them out in the left, and I left with the action of U L lambda P on psi K sigma, which again will give you up to a normalization constant, which will now appear in the denominator, and you will get psi of lambda P comma sigma prime. So what you are getting is that action of U lambda on psi P sigma actually will give you the D matrices, which are defined only for the Wigner's little group, and give you psi lambda P comma sigma. So can go to the next slide, please. So it shows that modulo these normalization factors, these matrices determine the C matrices as well. In fact, C can be identified NP by N lambda P D. And this is what is called the induced representation. That the subgroup in this case can induce a representation of the bigger group. Okay. Now let me make some comments about the normalization constant. The choice of normalization is somewhat arbitrary. It depends upon the chosen inner product. So if we choose the inner product psi K prime sigma prime, psi K sigma to be delta function, Dirac delta function K minus K prime delta sigma prime sigma, then D matrices can be shown to furnish unitary representation of the Lie group. So D dagger W, DW will be indeed by identity. It can further be proved that for arbitrary pair of momentum P and P prime, the above form of the inner product will persist, provided NP is chosen to be root over K naught by P naught. This is a simple matter. These details are there in Weinberg's book. Again, I'm telling you, the masterpiece. You should go through it, work out all the steps, you will understand it. Okay. But I'm just trying to give you a flavor. It is not possible to derive all the steps in a short span of time. Okay. So just go to the next slide, please. Okay. So now let me consider two situations physically realizable. One case is a massive particle in a signature convention, P square is equal to minus m square. And so for that, I choose the fiducial force vector. Since it's massive, I can go to the rest frame. And I can write down K mu as a column vector, 0, 0, 0, m. Column vector to save space, I am writing as a row vector and putting a transpose notation in the top, in the superscript, so that it is essentially a column vector. So 0, 0, 0 first, x1 component, x2 component, x3 component, x0 time component is the last one. So if you are dealing with a massive particle, you are entitled to go to the rest frame, where K mu will take this one. And for massless particle, you can take the, it will be, you cannot have a rest frame. So all that you have, the freedom is that you can choose, say, photon, you have the free to choose the direction of motion. You choose it to the x direction. So K mu will be 0, 0, kappa, kappa. Again, there should be a transpose, which is missing here. You should correct it on your own. Kappa represents the energy. So the momentum P3 component and the energy should be same. Okay. So we'll show that this little group, in this case ISO3, which is the Euclidean group, sometimes denoted by E2 also, a little group from massive particle SO3, which can be understood more or less heuristically quite well, because you can see that 0, 0, 0 m will be preserved by a matrix of this form. This block diagonal form, where the first block of 3 by 3 matrix is SO3 matrix, and the second one is a 0 everywhere except the diagonal one, which is 1. The action of this matrix on this thing will be M. So this is the little group. Little group for the massless case, you can easily understand it is given by SO3. Okay. Now let me go to the massless case. Massive case is SO3. From the massless case, we go to the massless case. So for the massive case, you can see it's a non-relativistic situation is again where you have the SO3 group or SU2 group, so which is the double cover of SO3. So you have all the representation half, 1, 3 by 2, everything. So whole apparatus of non-relativistic quantum mechanics can be brought here wholesale and applied here. But the massless case is different. It is a feature of relativistic quantum mechanics which is absent in the non-relativistic scenario. Okay. So let me go to the massless case now. Next slide. Yeah. So now the particle can be taken to be propagating along the z direction without loss of generality. Further, the energy scale I can choose in such a manner that it is 1 in some suitable unit. Again, this can be done without any loss of generality. So effectively, I'm setting kappa equal to 1. So K mu is the force vector 0, 0, 1, 0. So you see the third entry is the z direction. First entry was x direction, and the last entry is the time direction. So we are looking for the general structure of this W little group here, which satisfies this W mu nu K nu is equal to K mu. To determine this structure, it will be convenient to introduce the 4 canonical unit vectors: T mu, S mu 3, S mu 2, S mu 1. This is the way I have written. You see the structure. This everywhere it is 0 except 1 slot, and the last slot it gives you T mu. The second from the bottom gives you S mu 3. third from the bottom gives you sp2, and the top one will give you sp2. They are all unit vectors, but t mu is a time-like vector, and rest of them ss are space-like vectors. Okay? So this is a canonical basis I have chosen. Why I have chosen to work with this canonical basis will become clear immediately. So can you go to the next slide, please? So here T mu is a time-like vector, as I said, S mu is a space-like vector. Now to determine W, I have to determine all the entries. 4 by 4, 16 entries are there all total. And all of them are real matrices, subgroup with the Lorentz group, which preserves the K matrix. So let me assume the last column, the time column, so to say, because of 1, 2, 3 time, the 0th column you can say, is alpha, beta, gamma, delta. Let me assume that. Now you see T dot K, if you take the fold product, it will be T mu, K mu. So if you can expand further, T0, K0, both top, eta 0, 0. And the last component will survive. The third component will survive. So it will be T3, K3, eta 3, 3. Eta 3, 3 plus 1. And only this thing will survive. The time component only has a 0 component, 0, so it will be just minus 1, because T3 is 0. It is only the T0 which is equal to plus 1. And this Lorentz product is minus 1. It also means that Wt dot Wk is also minus 1, because after the action of the W, it is a Lorentz invariant. It is a Lorentz. Once you take the product of four vectors, it becomes Lorentz invariant. So Wt dot Wk is also minus 1. So now Wt mu acting on T, it will give you this thing, alpha, beta, z. I should have, instead of gamma, I have made a mistake again. I think it should be zeta. I changed notation all of a sudden. Instead of alpha, beta, zeta, delta in the first W, not gamma, delta. Okay. So yeah, this change. Okay. So now you employ these things. W mu. So you have Wt dot Wk will be also minus 1, and you will recover the last column, alpha, beta, zeta, delta. Also you means T dot K was minus 1, so Wt dot Wk is also minus 1. So you just simplify it, you will get just Wt, because you now apply Wk is K itself, because it's the definition of the little group. Now, so you expand it again, Wt mu, K mu. So Wt mu, K mu, eta mu nu. So again, the only surviving components will be Wt0, K0, eta 0, 0, and Wt3, K3, eta 3, 3. So you now substitute all the components, you will get delta equal to 1 plus zeta. So this will give constraint your this thing to time component and the spatial component of the last column. So delta equal to 1 plus zeta. Let's go to the next slide, please. So Wt, I can write an upgraded form, is alpha, beta, zeta, 1 plus zeta, and now you impose the normalization condition, because T mu was minus 1, so Wt mu also will be minus 1. Again, this is a Lorentz invariant thing. So once you impose these things and carry out the calculation in this manner, you see this will give you the form of alpha, beta. Next, zeta will be alpha square plus beta square by 2, and 1 plus zeta will be 1 plus alpha square plus beta square by 2. So now we have an updated form of W. We work with the updated form. What is the updated form? We have the last column we had already got. Next column, let us put it ABCD. We need to determine that. So now we let it act on S mu 3. Let us go to next slide, please. Yeah. 3, which has this form. No, just back, go back, one slide back. That's okay. So you see, once it acts on this thing, the second column from the right, that means the column for the z-axis, is recovered, ABCD, when it acts on sp3. Now you apply this condition again. W by sp3, W mu of W by S3 mu, W by S3 mu, W by S3 mu will be basically, since the Lorentz invariant is S3 mu, which is equal to 1. This will impose the condition that A square plus B square plus C square minus D square is equal to 1. I impose this condition that WS3 mu, WK mu should be equal to WK is basically K itself, so WS3 mu K mu should be equal to plus 1. That you can easily check, and then then you get the condition C minus D is equal to 1. Now you know that when you are dealing with this kind of orthogonal or pseudo-orthogonal matrix, all the rows or columns should be independently orthogonal and normalized. So WS3 mu with WT mu should be orthogonal to each other. But WT mu is T mu itself, and so you have to take the Lorentz invariant product S3 mu T mu, and this will give you 0, from where you can get this condition. Further simplification will result in these things. You will find that you are determining A to be minus alpha, B to be minus beta, and C to be 1 minus zeta, and D to be minus zeta. So all the entries of this column are now determined in terms of the entries of the time column. Okay, where zeta is equal to alpha square plus beta square by 2, as I mentioned earlier. Okay, so now please go to the next slide, please. Proceeding likewise for S2 and S3 in succession, you can arrive at a final form of W, which I call W alpha beta theta, which is the 4 by 4 matrices of this form. It is a simple thing, bit long maybe, but it is worth working out. Okay, this will be very instructive if you work it out on this. So the final form of W alpha beta semicolon theta, I put a semicolon to indicate they are of different nature than the alpha beta parameters. Theta is some sort of rotation, and alpha beta, as you see, corresponds to translation. Okay, so it will have this form. So you can, so what is interesting is that this W factorizes into two matrices. One is S alpha beta, another is R theta. Where R theta is the W itself, where you set alpha and beta to be 0. And S alpha beta, on the other hand, is W itself, where you set theta equal to 0. And they splits or factors into this form. And this is a very nice thing. Both of them form abelian subgroups of this Wegener's little group. Okay, not only that, let me go to the next slide, please. Not only that, you can show that if you conjugate these things by rotation matrix, S alpha beta conjugated by R theta, the way Professor Dashgupta was mentioning, you conjugate this thing, you will end up with S of alpha prime beta prime, where alpha prime beta prime is a rotated alpha beta. R theta corresponds to this cos theta sin theta minus sin theta cos theta. So here some rotation is involved. So it shows that it is an invariant subgroup. The entire S alpha beta is invariant subgroup. The fact that it is an invariant subgroup and it is abelian, it shows that it is not a semisimple Lie group. The corresponding Lie algebra is also not semisimple. Now let me find out what is the Lie algebra of this W. As I told you, all that you have to do, consider an element close to the identity and expand around the identity, retain the first order term, and then identify the generators. The SU2 example I had done explicitly. A more economical way is just to differentiate with respect to the parameter and evaluate at the origin. This is a better way of doing it. So you can find out the generators here, denoted by tilde. So you see this, I am putting tilde here because these generators as it in its form will give you this J3 tilde, T alpha tilde will be J2 tilde plus K1 tilde, and T beta will give you minus J1 tilde plus K2 tilde. The K1 tilde and K2 tilde, these are the so-called boost generators. They are somehow non-Hermitian, you can see. So these, apart from T theta tilde, T alpha tilde and T beta tilde, they are not Hermitian, although the J1 and J2s are Hermitian. But when you consider their action on the Hilbert space of one particle states, they will definitely be Hermitian from Wigner's theorem. So let me go to the next slide, please. So Hilbert space, when you write, we just remove the tilde. The corresponding generators will be just T alpha, T beta, and J3. And T alpha you can see is J2 plus K1, which I relabeled as A1, and T beta is minus J1 plus K2, which I relabeled as A2. One checks that if you calculate the real algebra, J3AI will be I epsilon ij aj, and A1 A2 is equal to 0. This algebra is quite reminiscent of your Poincare algebra in a miniaturized version, you can say. Because here you are talking about Poincare algebra in a Euclidean setting, and that too in a plane only. You have two translations like generators A1, A2, and they transform as two vector under rotation, SO2 rotation in the plane. Among themselves, they commute. So this is just a plain Poincare algebra in Euclidean setting in a two-dimensional, smaller dimension space. Okay. So given that A1, A2 are commuting, they should admit common eigenstates that you naturally expect. So apart from K index of psi K, they should have another extra additional levels AI, so that AI, capital AI, when it acts on this thing, it brings out the eigenvalue small ai's. But the point is that these A1, A2 can be subjected to the same unitary transformations. U of R theta, U inverse of R theta, and you get a rotated A1, A2. A1 means A1 will go to A1 cos theta minus A2 sin theta. A2 will go to A1 sin theta plus A2 cos theta. And once it happens, can you go to the next slide, please? You can construct the new states, rotated states, so to say, psi theta ki, which is U inverse of R theta psi ki, and you can easily check that when this A1 acts on psi theta ki, because A1 psi theta ki by definition is U inverse R theta psi ki, and you have now what you have done again, I have inserted identity operator U inverse R theta U R theta in front of this A1, and now I have clubbed U of R theta A1 U inverse R theta, and use the previous relation that it gets rotated. So rotated to U inverse R theta, then A1 cos theta plus A2 sin theta. So you can see that it will bring up the eigenvalue, which is rotated of A1 A2, rotated version of A1 A2. A1 cos theta minus A2 sin theta. So given any psi k AI as eigenstates, you are able to form a new eigenstate psi k AI theta, which will have a rotated eigenvalue along a continuous spectrum for A, because the same thing happens with the A2 also, as you can see. But this kind of situation, here we put an experimental input. Here we cannot go beyond theory. We do not have any indication about the existence of this kind of additional degrees of freedom, which is displayed by fundamental particles. We don't see any such experimental observation. We do not have simply any experimental observation to support that. So we simply demand these A vectors, I can club them form a vector A1, A2, both of them annihilates this psi Ka and gives 0. So they belong, so to say, in the kernel with eigenvector A equal to 0. So out of these three parameter uh, Euclidean algebra or ISO 2, I'm left with just J3, which can distinguish between different states. So J3 acting on psi k sigma will give you sigma k psi k sigma. This sigma is called the helicity and can be regarded as the component of J in the direction of P. Okay. So this is you can recall when we introduced wave fermion. It's appeared again. The slides. Okay. When discussing the wave fermion for the massless case, we found that uh, can you go to a slide? Okay. Uh, one slide black, we'll come to it later. Just one slide black. No. Ah, stick here. So this sigma, you can see that when it acted on this thing, this has a J3 was your like this P dot uh, n hat or something like that we had written, right? Acting on the two component oil spinors, it also produced eigenvalues on sigma dot p. Sigma dot p hat acting on shies produced eigenvalue plus or minus 1. Since the spin is half sigma dot p hat, so we identified the spin eigenvalue uh, with plus or minus half. Okay, so it's just this thing. So sigma is here, which is the eigenvalue of J3, which can discriminate between different states. Because the other, this A1, A2, will be completely useless because they just simply annihilate such states. Okay, and this happens only for massless particles. So J3 is nothing but you can see is the component J in the direction of P. Okay, can go to the next slide. So now you can see that if you apply the D matrix on psi k sigma prime, which is nothing but UW of psi k sigma prime, and W now factorizes within U also it will factorize because of group homomorphism U of S alpha beta U of R theta, but R theta is nothing but e to the power I theta J3 being an eigenvalue means operator whose psi k sigma being an eigenstate, so it will pick up the eigenvalue sigma and being a number it will come out, and thereafter I alpha dot sigma will going to hit psi k sigma. Since A annihilates these things, you are going to get e to the power 0, which is 1. So the eigenvalue e to the power I theta sigma will come out. So the action of UW on psi k sigma is nothing but e to the power I theta sigma psi k sigma. So this shows that under the action of W, the states by themselves are not invariant. It picks up an eigenstate. But sigmas are actually Lorentz invariant. Because I have chosen whatever frame you work with, because it doesn't depend upon which K you started with, what fiducial frame you chosen to work with. Okay. So finally you see, you ask the question, what happens when U lambda acts on psi p sigma? Because I have seen that the transformation property of the homogeneous Lorentz group is dictated by the transformation property of the little group itself. So I find that using this formula which I have derived earlier, you will easily find that taking normalization properly into account, which I have also indicated in the previous slide. So it will, the eigenvalue will come as some exponent e to the power I sigma theta, which now depends on lambda comma p, because it appears in W lambda comma p. Okay, and then psi lambda p comma sigma, because your action of U lambda will change the momentum content from p to lambda p. Okay, where theta lambda p occurs in W lambda p as these things. So again, I have written the factorized version of these things, where alpha, beta, theta all carries these indices lambda comma p. Okay. Can you go to the next slide? So final observation is that I have finished a bit early today. Final observation comments is that the translational subgroup of Ignorance neutral group can be shown to generate gaze transformation, which I have not shown. You can see some literature in this regard. I have also some couple of papers. Should you be interested, you can contact later, and then I can send you some earlier paper. Also, there are some references to earlier works in this direction where you can find it. As I mentioned, the helicity sigma, despite its appearance here, so it seems, I have not argued anything what value sigma can possibly take. It seems that sigma can take any arbitrary value for massless particle. It was restricted for massive particle because I got SU2 group as a stability subgroup from SO3 or SU2, whatever you say. So the different spin states will be indexed by the SU2 indexes, which are necessarily restricted to half of odd integers or integers, whatever you say. Huh? But in the case of the massless particle, it seems that sigma can be allowed to take any possible values in the continuum. But this is not true. There are some topological restrictions, which again I am not able to go into here because of lack of time, and it is a bit non-trivial also. There are topological restrictions which allows only integer and half of integers. For example, in the case of well spinner, you see that the helicity indeed comes out to be half integer. Okay. So when neutrinos are massless, means before mass of the tiny mass of neutrinos were detected, neutrinos were thought to be described by well spinners, and their helicity states were half and minus half. For neutrinos, it was half, and anti-neutrinos minus half. Okay. And as I said, sigma is Lorentz invariant, but not the states themselves, so they pick up helicity dependently expected. Let's go to next slide. Okay. So here there is another point. This you may ask the question that for neutrinos, as I just said, it is plus half and anti-neutrinos is minus half. Means why are you calling it anti-neutrinos? You could have said just neutrinos, left-handed and right-handed neutrinos, that same species of particle. For photons, for example, helicities are restricted to +1 and -1. Gravitons, which are of course not detected yet, but they are postulated to exist in a linearized theory of gravity and a quantized linearized theory of gravity. So helicities are expected to be plus or minus 2. So means here I don't say left-handed photons or right-handed photons. I identify all the photons. But for neutrinos, I am discriminating. The answer is that these theories which describe photons are electromagnetic theories which are parity respecting, like gravity also, general relativity respects parity transformations. So the way we have constructed Dirac equation, we have enlarged it by including the parity to provide an irreducible representation of the Lorentz group enlarged by incorporation of parity. So here also you can do the similar thing. The symmetry is much bigger. So it tells you that invoking parity, you can go from plus helicity state to minus helicity state and vice versa. So they are regarded as the same species of particles. But while neutrinos, they participate only in the weak interactions, which are parity violating theories, as we know. So there is no way you can make use of the parity transformation, convert a state of neutrino to the active state of antineutrino. Because those transformations are simply not available in your theory. So they are regarded as different species of particle altogether. Finally, just classically speaking, you have studied polarization of light. So right polarized or clockwise or anti-clockwise polarization, circular polarization to say, circular clockwise or anti-clockwise. So they will correspond to plus minus helicity states. So this is a classical picture, and plain polarized light can be obtained by considering suitable linear combination of these circularly polarized rays or vice versa. Okay, so that's all I wanted to say. So you can see that Wigner's little group really plays a very important role dictating the transformation property of one particle states when you subject them to Lorentz transformation. You cannot just ignore saying that, oh, it is a tiny group, little group. It is not so. These groups play a very, very important role. And in quantum field theory, construction of quantum field theory is, in fact, Weinberg's book, he has provided a novel approach to quantization of quantum field theory. Means he wants to show that quantum field theory is an indispensable theory if you want to have a merger of both relativity and quantum mechanics. So here he started from the particle perspective and described how multi-particle states transform under Lorentz transformation. And for that, he had to necessarily include or incorporate the transformation property of this Wigner's little group. As you can see, their structures are quite different for massless and massive particles. And what happens further, I have discussed the Pauli Lubansky vector W mu, but I could go to the rest frame and show that it is proportional to W mu is proportional to S into S plus 1. But this, strictly speaking, holds for massive particle, because you can go to the rest frame. For massless particle, on the other hand, you cannot go to the rest frame. So you ask the question, what happens to W mu in this case? The answer is that, I cannot prove it, but the answer is that W mu is proportional to P mu in this case. And this proportionality factor is precisely helicity. Okay. So with that, I conclude. I would like students to ask questions if there is any. Any question? Submission.
I have a question.
Yes, sure.
Yeah. Okay.
Since the Wigner little group correspond to the maximal subgroup of the Lorentz group that leaves the core momentum of the relativistic particle invariant. So my question is that what happened for the lower dimension space time for the is it exist any little group for the Lorentz group? And
we have in our papers, we have found out little groups in lower dimension. You can see some of my earlier papers written in early 2000.
In 1 plus 1 is in 1 plus 1.
1 plus 2 dimension, please. 2
no,
plus
1 plus 1. For is it
1 plus 1? I don't think you will have any little group.
Why? Any argument?
Not immediately. I have to think over it, but I don't think you have, because 1 plus 1, the Lorentz group itself is only one parameter group. You cannot have any non-trivial subgroup.
Okay. Mm-hmm.
Anything else? Mr. Bishash, there is some Bishash who seems to take a lot of interest, ask a lot of questions. Sumit Bishash.
Hello, sir.
Yes. Sumit Bishash, can you tell me where are you from? Which institute you are from?
Professor, I am from University of Dhaka, Bangladesh. I am from Bangladesh.
Oh, Bangladesh. Oh, okay. Very nice. Yes,
okay. I am currently doing my MS here. So I am highly interested in high energy physics and cosmology, and this particle physics part seems pretty interesting to me. And I want to say that these classes are so much helpful for me.
Very nice.
I'm
very happy to see. So you have got these links. Means you had applied earlier.
No. Even in my application, I did not know that this workshop is going on. Then our Professor Arshad Momin sir was sharing this, that Professor Balachandran will give a talk. Yes. Then I immediately asked for permission to Professor Bose, and she helped
happy
me.
To see. Okay, very good.
It's an honor, sir, to do your classes.
Okay. So
I didn't know that it has gone via Arshad. I didn't know how Shumit got the information, because he just wrote me a mail and I just invited him. I didn't know that it has gone via Arshad.
And I was just Asha sir was sharing the information in Facebook, and then
Okay, okay. It's nice. It's
I
very nice actually.
I took I just picked that and Google the name the where the group theory seminars are going to be held in India, and then I found it and then I immediately mailed you, madam.
Yeah, yeah. Thank you so much for doing. I mean, this
No,
and
no, I mean,
Very
thank you so much.
yeah, you are asking lots of questions. It's nice that that interaction is the major part of this type of workshops, right? So
you,
any
you can
participant.
think that this seminar, this workshop, how much useful is to me, because group theory, I didn't do a course on group theory, but du- during studying standard
can,
model, I could see that the without group theory.
can you can you can I have a look at your face? Please
Yes, yes,
open the video.
of course, Professor.
On the camera.
Come. Very good. So,
I
so
want to have a look of the speaker also, so I can take a photo.
no, it's okay.
Please, please.
I think. So, no. It's the question. Please ask the question. Please, what question you have?
No, I think I have to read the Weinberg book thoroughly. Then this was pretty clear, but I think the topological facts that you're
Yeah. That is
I should
more
go
involved.
through it. Yes,
Yeah,
yes.
yeah. He has given a very nice discussion about it, and his book is extremely thorough. I tell you, if you want to learn field theory, there are three books: Weinberg, Intersection Jubar, and this Peskin and Schroeder. These are three.
Yes.
Apart from there are other books also in the market, many of them, but these are the masterpieces. Okay.
I actually
Which
I was following Peskin Schroeder, but Weinberg book. After your class, I looked at Weinberg book yesterday, and it was so nice. I think the second chapter actually, it I think it will help a lot the Wigner group, because unitary representation of this Poincare group, because every particle I read that carry irrep of Poincare groups, and this non-compact group and the unitary representations of this non-compact group. I wanted to learn that, and the classes are so much helpful.
which part of Bangladesh you are from, by the way?
I am from Dhaka. My hometown is actually in Kushtia.
Okay. Very good. Any other questions? So, Sumit Biswas, please keep in touch. I'll be happy to help you if you want.
Yes,
Whatever. Okay.
surely, sir. It will be very much helpful to have all of you in my life.
No. It's very happy to see somebody from Bangladesh participating. And Arshad, I know him for quite some time, although I'm not in touch with him for many years now. But please convey my regards to him. Okay.
Okay, sir. Of course, sir.
Anybody else? Okay, if there is no further question, let us
Stop here for now. But I should thank you for a nice 3-lecture series. It should have been 5-lecture series, continuing a little bit more, going more to little groups. But anyway, we have a fixed time frame, so that was difficult to.
Yeah. No, means I just wanted to give them a flavor. Means,
Yeah, so that they
then
can
they
pick
can
and
go through the
read.
books. Yeah. That's in fact the purpose of the whole workshop is that you cannot expect to teach them everything.
Definitely, you
In
cannot.
fact, the Professor Dashgupta, the way he went, he detailed, worked out things. It was very good, but it takes long time. This is 6
No, but
lectures.
that was one way good that some people are there who are very new to group theory. They have never had a course in group theory formally. So, like it was also helpful for them to pick up and then, glimpse of otherwise.
It was a fantastic job. I think people means it was basically designed to help the students from the northeastern part who are geographically live in a very isolated and remote part. But I feel a bit sorry to say that not many participants are from northeast. So and this whole exercise becomes futile some otherwise. But of course,
Yeah, and
means, since Assam University are organizing it, I expected a lot of students from Tripura area also.
unfortunately, no
Also,
student from Tripura. No student.
yeah,
No
yeah,
student,
yeah,
no faculty, if I am not wrong.
yeah.
So,
This is
so far I can
major sad.
remember, I could see Ishwar Chandra, who is from Imphal, and then I could see Diptiman Neo from Arunachal. Then I could see somebody from Tezpur University, but not many of them. Not many.
One Prasad Boshu is there from Cotton University, but
Yeah,
he is not
they,
actually from Northeast. He
yeah,
is a
that
very
is
much
true.
West Bengal guy. So he was in fact our student in Assam Bose Center, and then he
Great.
did his PhD under one of our ex-faculty, Sandeep Chakraborty, and now he
You
is
have,
there in Guwahati. But I
okay, we
wanted
have, yeah.
genuine Northeastern people because they are really not exposed, and is this kind of uh, thing means we seldom get an occasion where such a good set of speakers are speaking.
That's very true. I mean, some people wrote me mail saying that their classes have started and they have to write exam this month. I was very surprised which exam they have to write this month. I don't understand. But anyway, if they're telling that might be there something. So our MSc students are participating, some of them, not all. And I don't know where the end semester exam is going to happen right now in the month of November. I don't know. Maybe December one they are meaning, but yeah, they told that the class schedule that they should have told earlier when I sent an invitation, but somehow